Hello and welcome everyone to the second lecture on aggregates. So last week, or whenever you watched the last video, we were talking about what were aggregates, namely that they're crushed rock or small particles of rock, and how they have different properties. We talked at length about porosity, which is the ability for a rock to absorb water. This means water will react with positive and negative charges inside the chemical composition of the minerals. It's not water sitting on the surface. We also talked a little bit about the density of aggregate, and we talked also about bulk density. And then we also talked a little bit about different kinds of rock geologically. We talked about limestone and sandstone and granite and how they can vary too. We also had a very important rule of thumb. Generally, the more dense an aggregate is, the less porosity it has, and therefore the more durability. It will last longer. And the second rule of thumb is the more dense an aggregate is, generally the stronger it is. And we're going to go into that second rule of thumb right away. Now, strength can vary depending on what kind of strength we're talking about. Now, we've got some diagrams here in the right-hand side of this lecture slide. We can see with the first one, A, that is compressive strength. Imagine you have a rock particle, an aggregate particle, and it's being squeezed, it's being pushed. Now, aggregate is very strong in tensile strength. Compressive strength, sorry. B, tensile strength is where it's being pulled apart, and aggregate is really, it has no strength in tensile strength unless the aggregate particles are bound together with a cement. Basically, they will just pull apart because really they're not being pushed together, they're being pulled apart. Now, shear strength is where you've got opposing forces, but they're on different planes. And there is some strength in aggregate, but not as much as in compressive strength. Now, remember with this, with shear strength, this is a very important property that you measure a lot when you study geotechnical engineering or geomechanics. So remember that for when you do that in UG2, UG3. The final one is flexural strength. Imagine you have your aggregate laid out in a big cuboid like that, and you've got support forces at the bottom and a force coming down in the middle. Well, the top of that beam will be in compressive strength, the bottom will be tensile. So again, aggregate does not have a lot of strength in tensile. So remember this. The strength of an aggregate is very much in compressive strength and shear strength. We do not really consider flexural strength or tensile strength for empty aggregates because basically they will fall apart immediately, unless of course the aggregate is bound together with a cement or some kind of binder, as is the case in concrete. Now, in concrete, the tensile strength of a concrete is determined by the tensile strength of the cement, not the aggregate, because it will break at the cement before it breaks at the aggregate. Likewise with the compression, it will break in the cement before it breaks in the aggregate. So actually in concrete, for normal concretes anyway, where the aggregate is stronger than the cement, we are not actually interested in the strength of the aggregate. Now, finally, the orientation of sedimentary particles can influence the shear strength. So remember, if there are lots of voids, because you've got sedimentary aggregate and it's a flaky shape, then that can really reduce the shear strength. It can reduce it, as well as compressive strength, because air does not give any strength to an aggregate. So let's now look at different sizes of aggregate. Now, generally, aggregate is sorted into different sizes, with a rock crusher having different settings, or with a sieve. Now, the size of an aggregate is basically based off the average diameter. Look at those aggregates there. Are the particles circular or spherical? Of course not. But the average diameter is basically, if we were going to take a cross section at various points and we were trying to cut that particle in half, at any point the average diameter or average cross section would be the average size of the aggregate. So we've got different kinds of sizes, and they typically range from, these are very typical aggregate size: 5mm, 10mm, 20mm, 40mm, 80mm, and 120mm. I will also say that increasingly 25mm aggregate is becoming a very common size these days. Now, 5mm aggregate is very small, and you can sort of see an example of that down in the bottom right hand corner, with maybe the second circle, the second from the left. That would be 5mm aggregate. Those particles have an average diameter of about 5 centimeters. 10, 20, 40, 80 millimeters, the same could be said. 120 millimeters, suddenly the aggregate particles are getting very big, and we use that for a special purpose. We use that for filling in gabion baskets. And I've given you a picture of a gabion basket wall in the bottom left hand corner. And so these are basically steel meshes in the shape of cuboids that are filled with rock, and then you can actually arrange them to make walls, and they make really good retaining walls for holding back earth. You'll sometimes see these on the side of motorways. I think there's a few gabion walls on the upper highway going through Gully Ali Beg. Now, they need to be quite big, because otherwise they would fall through the gaps of that steel mesh. Now, sand has an average diameter usually ranging between 1/4 to 1 millimeter. Normally the sand that we have here in Kurdistan is quite coarse. It's usually around 1 millimeter in average diameter. And silts and clays have a much smaller average diameter. They can be anywhere around 10 to 200 microns. So they're quite small. So that's about 0.001 millimeters. That's as small as clay would get. Now, there's an issue with size that we need to take into account here. Oh, one thing I do need to say about size is that can influence the strength of the aggregate. Remember, the aggregate will be stronger in compression and tensile and all directions, but compression really is what we're talking about here. The lower the void content is, the lower the void ratio. So obviously, if you have an aggregate where the particles are all the same size, the smaller the particle size, it will have less void content, and so generally it will be stronger. Now, we need to talk about what happens when all of the particles are not the same size in an aggregate. Well, if they are all the same size, that's what we would call poorly graded. Other names for this would be open graded or uniformly graded, and you can see that with the middle section there. And you can see it's got big voids going between the particles. Now, on the other end of the spectrum, on the left, you have well-graded aggregate. Now, this is where the aggregate particles are a range of different sizes. And you can see, and another term for this is densely graded. And you can see there that there's actually very little in the way of void content. Now, just quickly, what would be stronger if you have two aggregates which are identical in all other means, but you have one that is well graded and one that is poorly graded? Which one is stronger in compressive strength? Which one would you be laying down as a foundation for building a high-rise building? Well, obviously, it's the well-graded aggregate because the void content, the air gaps, are much less. The percentage of air in that is much smaller. Now, with well-graded, one issue with well-graded is sometimes the way they make it is basically they will get crushed rock from a quarry, and they will be putting it through a sieve of say 20 millimeter opening, and that will mean that it will have everything in between that is smaller than 20 millimeters falling through, and you end up having a well-graded aggregate where the largest particles are 20 millimeters and the smallest particles are tiny. They're microscopic. They could be only 10 microns in diameter, really small clay particles. Now, we can use that aggregate for many things, such as foundations for buildings, but one thing we would not be wanting to use that for would be concrete. The reason we don't want to use that for concrete is because the smallest particles are clay and organic silts, organic soils, and these particles have very high porosity. And so we want to be rid of that somehow. So one way we can do that is we could have sieve it a second time, and anything smaller than say 0.5 millimeter you throw away. And then you've got a well-graded aggregate, which is anything between 20 millimeters and 0.5 millimeter. That would then be a good aggregate to use for concrete. Another way to make an aggregate suitable for concrete is to do something called gap graded. This is where we get two sizes of aggregate and we mix them together. And obviously it's much easier to make gap graded than it is to make well graded, because you don't need to put it through sieves. You can get two different sizes of aggregate, then mix them together. And really, this is a much more convenient way to get an aggregate that has a very low void content. The other advantage of this is you've got much better quality control. You can make sure you use a hard 5-10 millimeter aggregate as well as sand, let's say, and you can make sure that there's no soil, there's no clay or anything that has high porosity in it. And that way you've got an aggregate which is really good for concrete. Remember how we said porosity leads to poor durability, and if you're using it in concrete, that it will lead to lots of cracks in the concrete. We don't want that. That's why when we do eventually make concrete, either in this module or in concrete technology, we're going to be making gap graded aggregate for the concrete. We will be mixing 5 to 10 millimeter stone with sand. So that's what we mean by gradation. Well graded, there's a range of sizes. Poorly graded, there's only one size or a very small range of sizes. Gap graded, we have 2 or maybe 3 different sizes mixed together. So how do we test how well an aggregate is graded? Well, we do this using a sieve analysis. And I'm going to upload a video onto Moodle. There will be a YouTube link showing a sieve video, a sieve analysis happening in real time. So basically, what we would use would be that machine there in the bottom left-hand corner, and we will be vibrating a series of sieves. And these sieves will have different openings. The ones on top will have the biggest openings, and the ones on bottom will have the smallest openings. And it could be anywhere from about 40 millimeters down to about half a millimeter. And we will place a sample of the aggregate in the top, and then we will shake it. And different portions of the aggregate will get stuck in different parts of the or in different sieves. So if you have a particle of aggregate which is let's say 35 millimeters in diameter, it's going to fall through the 40 millimeter aggregate, but it's going to be caught by the 40 millimeter sieve, sorry, but it's going to be caught by the 25 millimeter sieve. It's going to sit in that sieve. And after that, we can tell if it's poorly graded or well graded or gap graded by taking basically the percentage of aggregate which is caught in each sieve. And we lay it out using a logarithmic scale, and you can see it there. On the x-axis, we've got the particle size ranging from 100 millimeters to 1 micron. And then on the y-axis, we've got the percentage. So this is the percentage of aggregate which is smaller than this than a sieve size. Now, if it's poorly graded, all of the aggregate is going to be caught in 1 or maybe 2 sieves, and you're going to end up with a really long straight line where you see 1. If it's well graded, then the aggregate is going to be evenly distributed across all sieves, and you end up with that nice slope, that incline with number 2. If it's gap graded, you're going to get all of the aggregate concentrated in 2 different sieves, a sieve with a small opening and a sieve with a big opening. And that's where we get this step inside the curve. You can see it sort of goes up in a big step. That is an indicator of gap graded. So here's another example. We can see here 3 different aggregates. One is gap graded, one is poorly graded or uniformly graded, and one is well graded. So let's look at the well graded initially. Now the well graded, if we were to say learn anything about this, we would say that 60% of the aggregate is smaller than 10 millimeters. We would also be able to say 30% of the aggregate is smaller than about 0.6 millimeters. So 30% in mass we're talking about here. Do you see how I'm getting that? I'm going to the y-axis, and I'm seeing 60 there, which is percentage which is smaller than, and then I'm going across to the curve and then coming down onto the x-axis and seeing the the size of the sieve there. So what this is telling me is that 60% of the aggregate is smaller than 9 millimeters, or 10 millimeters, sorry. 30% of the aggregate is smaller than 0.6 millimeters, and 10% of the aggregate is smaller than 0.02 millimeters. So with this well-graded aggregate, in this case there's actually quite a bit of clay and sand inside it. Now with the poorly graded aggregate, the uniformly graded aggregate, sorry, all of the aggregate is between 1 millimeter and 0.1 millimeters in average diameter. There's no big particles in it, there's no small particles in it. So we can see that there's no big stones, and neither is there really small silt or clay. This is a very pure sand. With the gap graded, we can see how you've got that sort of step, you've got that wave pattern in it. And so you can see that there's a lot of aggregate which is around the sort of 5 millimeter diameter size, or anywhere between sort of 1 to 10 millimeters. And then there's also a lot of aggregate between that sort of 0.1 to 0.01 millimeter diameter. So in this case we really have some big stones mixed with silt. So that's an example of a gap graded, a poorly graded and a well graded aggregate, and how it will look. Now in the in your second assignment, you're going to have to plot this, and you're going to have to tell me if the sample aggregate that I've given you is actually well graded, uniformly graded or gap graded based on the shape of the curves. Now this is an example of the sieves used in the sieve analysis. So you can see there we've got sieves which are all different size openings, and we arrange them on the machine. We stack them up, the largest opening on top, the smallest opening on bottom, and we put our sample inside the top, and then we vibrate it. And then you can see the final sample. It's got the biggest particle stuck in the top sieve, and the smaller ones will be falling down. So again, with a well-graded aggregate, you're going to have an equal mass of aggregate in each sieve, just about. A poorly graded aggregate, all of the aggregate is going to sit in one sieve or two sieves. Gap graded, it will be in two sieves that will be separate in size. And again, I've got a video of a sieve analysis loaded up on to the Moodle page. Please check that out. So here's an example of a sieve analysis. Now one thing you need to know about a sieve analysis is that the sieves always come in standard sizes. And they're really confusing sizes. They are 37.5 millimeters, 19 millimeters, 9.5 millimeters. These are odd openings. Why aren't they 40 millimeters, 20 millimeters, 10 millimeters? Well, the reason for this is that the science of a sieve analysis was developed in America. And in America, they still don't use metric units. They still use imperial units. And so they based their sieve openings off inches rather than millimeters. And so that's why we have very odd opening sizes. That's just something you need to be aware of. Now, when you do the sieve analysis, you first take your sample and you weigh it. And then you place it in the sieves and you shake it, and then you weigh the amount in each sieve. Now that will be a percentage of the original weight. You take the total cumulative weight of particles passing through each sieve. So this is the entire weight of the aggregate that is smaller than that sieve, that fell through that sieve, and you divide it by the total mass, the original mass. Now, if all of the sieves if you take all of them together and you take all of the masses, the cumulative masses, and that is different from the original mass by more than 0.3%, that means you've lost some of the aggregate, or some aggregate fell in. This is called a wash test. It's a way to ensure that the sieve test you're doing is accurate, that it hasn't been corrupted by some of the mass of the aggregate being lost and falling out of the experiment. So if it's greater than 0.3%, the wash test, it means you need to do the sieve test again. And then once you do this, you can take the cumulative passing percentage of each sieve and you plot it on semi-log paper like we saw before, and then you can join all the dots together and make a curve. Now, there's something called the D10. The D10 is basically the sieve opening, or the hypothetical sieve opening, where 10% of the particle mass will pass through. So any particle that falls below this 10%, it means it's the 10% of the total mass of the aggregate, which is smaller than the other 90% of the aggregate. That's what the D10 is. It's the 10% diameter. You can also find the 50% diameter, where half of the aggregate is smaller than this diameter and half is bigger than this diameter. The D60, 60% of the aggregate is smaller than this diameter, 40% is greater. Now, the D95, or the 95 percentile diameter, is called the nominal maximum size. That we can't go through the aggregate and look at every single particle and find what is the biggest size. So the D95 gives us an idea of the nominal maximum size from our sample. Now, the uniformity coefficient is a ratio between the D60 and the D10. So let's say the D60 is actually about 5 millimeters, let's say. And the D10 will be much smaller, of course, because only 10% of the aggregate is smaller than the D10. Let's say that will be 0.5 millimeters. What would the uniformity coefficient be in this case? Well, it would be 10. It would be 5 divided by half. It would be 10. Now, an aggregate is considered well graded if the uniformity coefficient is more than 5. If it is lower than 5, it is considered uniformly graded or poorly graded. So remember, the way to determine if an aggregate is well graded or poorly graded, it's not just from looking at the curve on your plotted graph of the sieve analysis. There's actually something called the uniformity coefficient, and this is just a stock standard way of determining if it's well graded or poorly graded. Obviously, if it's poorly graded, if it's uniformly graded, the D60 and the D10 will be very similar because all of the aggregates are going to be about the same size, in which case the uniformity coefficient will be very small, and it would be lower than 5 would be considered uniformly graded or poorly graded. Now remember what I said before about how often with aggregates we prefer to use gap graded rather than well graded. The reason we may not want well graded is that the really small particles, which are smaller than a tenth of a millimeter, those will usually be clay, silt, organic soils, and all of these really fine particles tend to have very high porosity. And so remember, high porosity will mean that water will react with it, it will get stuck inside the particle and it will break it down. This will mean the aggregate is less durable. So if you were using a highly porous silt inside concrete, it will cause the concrete to crack because the water would basically expand the particle. And that's why when we make concrete we use clean sand. We can't have dirt or soil inside a concrete. It makes it really weak. Now, one of the things you can do if you have a well-graded aggregate but you don't want it to have high porosity, one of the very simple things you can do is called the D10 cleanse, where basically you take the 10% of the aggregate, which is the smallest, so you put it through a big sieve, and the smallest 10%, you throw it away. You do away with it, and basically you're cleaning the aggregate of the organic soils and the clays and the silts and all of these really undesirable particles which have high porosity, and then you're just left with sand and crushed rock, which is much more stable and it has much less reactivity with water. That's called the D10 cleanse. So this is an example of a sieve analysis. Now I'm going to click the animation here and show you the results. If you want to do this in your own time, then what I recommend you do is you just pause this video right now and you try and have a go yourself. But let's do the sieve analysis here. We can see on the left hand side column we've got all of the sieve openings. So the biggest sieve opening in this experiment is 4.75 millimeters, and the smallest opening is 0.075 millimeters. And then there's also a pan, just a tray to catch anything smaller than that. Now we can see that after the shaking there's a mass of the sample caught in various sieves. So the 4.75 millimeter sieve, that left 9.76 grams of the aggregate in that sieve. Everything else was smaller and it fell through. The 2.36 millimeter sieve, that held 59.63 grams of the aggregate and everything else fell through, and so on and so on. And the total mass of all of those sieves and the pan put together was 1,375 grams in total. Now this is interesting because if you look at the number one question, the original mass of the sample was 1,378 grams. So where did the other 3 grams go to? Well, these are it's probably just dust which has gone airborne, or there may have been a small particle of rock that fell onto the ground and was lost. We don't know. But those errors can actually cause big issues. So we need to do a wash test here to make sure that the final weight is not too different from the original weight. So we need to make sure that the final weight is no more then 0.3% different from the original weight. So there's a calculation you do there. It's 1,378 minus 1,375, so 3, over 1,378, and that should give you a percentage. Now, let's fill in the gaps here. So, of the 1,375 grams, 9.76 grams were caught in the 4.75 millimeter sieve. You can see that in the first row. So the difference is 1,365.24 grams. That is all of the aggregate that fell through the 4.75 millimeter sieve. Now, that's the difference between 1,375 and 9.76. And we can go through the various columns here and figure that out. So with 2.36 millimeter sieves, the second column, we're trying to work out the entire mass, which is smaller than that. So that'll be 1,375 minus 9.76 minus 59.63. The 59.63 and the 9.76 are the masses that were caught by sieves larger than 2.36 or 2.36. So 1,305.61 grams passes through. Now, following that, we can do a percentage passing. So this is basically the percentage of the 1,375 grams that is smaller than the sieve size. So the 99.29 there, that is the percentage of 1,365.24 over 1,375. That's the percentage passing through. So we can see that 99.29% of all of the aggregate particles are smaller than 4.75 millimeters in diameter. And corresponding to that, we can do the percentage retained, which is basically 100 minus the percentage passing. So only 0.71% of the aggregate is larger than 4.75 millimeter diameter. So that's basically the sieve analysis. Following that, we can take that final column and we can plot it on semi-log paper provided. Another question we need to ask ourselves following the logging and making that graph is, what is the nominal maximum size? What is the D95? Also, what is the coefficient of uniformity? Well, first off, let's do question 4 here. The nominal maximum size is where 95% of the aggregate is smaller than this. Well, we can look at the percentage passing column and we can see that 95.63% of the aggregate is smaller than 2.36 millimeters. So the nominal maximum size will be about 2.3 millimeters roughly, or maybe 2 millimeters. The coefficient of uniformity will be D60 over D10. The D60, well, you can see that when the sieve size is 0.6 millimeters, 68% is passing through, and about 36% is passing through when at 0.3. So if we were going to plot this, we would probably find that the D60, where 60% passes through, the sieve opening is probably about 0.5. millimeters. The D10 is clearly smaller than 0.15 millimeters because 20% passes through, but it's larger than 0.075 millimeters because only 1% passes through. So I'm going to say that it's probably about 0.1 millimeters. So what's the coefficient of uniformity? It's 0.5 over 0.1. So the coefficient of uniformity is 5. So we would consider this well graded. There's a range of different sizes. Now, let's talk about well-graded and gap-graded aggregate. What would we use this for? Well, when it's well-graded or it's gap-graded, it has a very low void ratio. So that means it's got very high compressive strength, which means it's very good for actually using for road bases or building foundations. It's also very good for concrete. Now the reason for this is that concrete is a mixture of cement and aggregate. Now aggregate is the stronger part of concrete, cement is weaker, so obviously if you can have a higher proportion of the aggregate, of the concrete being aggregate, it's going to be stronger. Also, the cement is very expensive, the binder. It costs a bit of money. And therefore, you want to have an aggregate that doesn't have big voids that need to be filled with cement because it will be more expensive. Now, one of the other things with well-graded and gap-graded aggregate is that it can actually bulk up. So you can have big voids inside. If you just pour it out onto the ground, you can then stand on it and press it down because big voids may be inside that aggregate unless it's been compressed, meaning that you haven't pushed the smaller aggregate particles in between the larger aggregate particles. And this is where we would use something like a sheep's foot roller, similar to that sheep foot roller that you see in the top right corner. It's compacting the aggregate so that you can take out all of the air voids so it has a high compressive strength. That's why you need to do this when you're building a road. You're pressing down on the well-graded or gap-graded aggregate using a compactor in order to give it that strength. If you don't do that, then it won't be strong. Now the other thing is with well-graded, sometimes the way they make well-graded is with something called apex, where basically they will put the aggregate through a sieve. So you can see in the bottom corner there, Apex 65, AP65. That means they've put it through a sieve with an opening of 65 millimeters. So anything smaller than 65 millimeters is inside that aggregate. Now obviously that's going to have a lot of really microscopic particles. It's going to have things like clay and silt and organic soils, and all of those really small particles have very high porosity. Now generally, depending on what we're using it for, we may not want high porosity because that really lowers the durability of the aggregate. And so for something like concrete, where you don't want porosity because it will react with water and cause the concrete to crack, we usually for concrete we would use gap graded instead of well graded. Now uniformly graded has a very high void ratio. Look at that uniformly graded aggregate in the top right picture. you can see all of the gaps in between the rocks there. All of the rocks are about the same size. Now, one of the good advantages of having an aggregate that is high in void ratio is it's really good for drainage. Imagine if it was raining, and it was raining on that aggregate. Is it going to form puddles on the surface? No, it's going to infiltrate into the ground. So this is one of the things that they look for potentially soils for football fields. They will make sure the soil has a very high void ratio. One, because it helps the grass grow, but also because when it rains it doesn't form puddles on the surface. So they will use a soil that all the soil particles are roughly the same size. The other great advantage of uniformly graded aggregate is that it's very self-compacting. This means that you do not need to press it with a compactor or a roller. When you pour it onto the ground, it automatically self-compacts. All of the rocks, which are the same size, will fall into a matrix like ball bearings, and they will minimize the void ratio. So an advantage of this is that if you have a big hole in the ground that you need to fill, this picture in the bottom right is a sinkhole that emerged in Japan. Now, what are you going to do to fix that hole? Well, obviously you need to fill it in with an aggregate, and then you can build the road surface again. But you can't fill it with a well-graded aggregate, because if you did that, you would need to compact it, and there's no way you can get a roller down there to press it and compact it. But if you filled it with a uniform graded material, it would just fill up like ball bearings, and it would like marbles in a bucket, and you won't need to compact it. It will be self-compacting. And then on the surface you can place a well-graded aggregate to give strength for the road, and then you can put your asphalt surface down. Now, one of the disadvantages of uniformly graded is that it's got a low compressive strength because it's got all of these air voids inside it. And if you've got these air voids, the air doesn't give it a lot of strength. Air, there's no strength. And therefore, we wouldn't use a uniformly graded for something such as concrete, or for a road base or a building foundation, things which require high compressive strength. Now, another advantage, or a use for uniformly graded, is that it can be used for wastewater filter treatments. This is where you're basically pouring wastewater or sewage over rocks, and basically the rocks have a layer of bacteria on them, and the bacteria basically eat away the sewage, and so they clean the water. Now, there is a wastewater treatment plant in Erbil which broke down many years ago in the time of Saddam Hussein, and this is one of the reasons why you will get sick if you drink the water out of the tap here. That's why everyone has to drink bottled water. In the developed world and Erbil in time, you have wastewater treatment plants and drinking water treatment plants which stop this, so you can drink water straight out of the tap, and it's fine, it doesn't make you sick, it's pure water. Now, they would use uniformly graded aggregate for this because basically the water can infiltrate through the aggregate. It won't form puddles on the surface. So that's just one other use of uniformly graded aggregate. And finally, I'm just going to finish here for now. We've got an example of a building standard or an engineering standard. This is the type of aggregate that needs to be used for concrete according to the ASTM standards. That's the American standards. So we can see the different percentages in that scan of aggregate that can fit for different sieve sizes. Now obviously you can see that the aggregate for any concrete needs to be gap graded or well graded. There needs to be a range of sizes, and that's so you can minimize the amount of cement you need to use, and that means that the concrete will be stronger for a given amount of cement, and it will also be cheaper because cement's really expensive. So that's just an example. I hope you've enjoyed this lecture. Please contact me by email or phone call or during the Zoom tutorial later this week if you have any questions. Thank you so much. Bye.
In this video, we are going to take a look at the Los Angeles test, which is a measure of an aggregate's strength, or more precisely, its resistance to fragmentation. The principle of the test is quite simple. A 5 kilogram sample of 10 to 14 millimeter sized aggregate is placed in a rotating drum along with the 11 steel balls. The drum is then set to rotate for 500 revolutions, after which the degree of degradation is measured by using a 1.6 millimeter sieve. The more material that passes through the sieve, the less resistant the aggregate is to fragmentation. Now let's take a look at the test in more detail, starting with sample preparation. The sample sent for testing must contain at least 15 kg in the 10 to 14 millimeter size range. Only material passing a 14 and retained on a 10 millimeter sieve is used. In addition to this, either 60 to 70% of this material must pass a 12.5 millimeter sieve, or 30 to 40% must pass an 11.2 millimeter sieve. The sample must be reduced to create two size fractions by using just one of the intermediate sieves. The two size fractions are then washed thoroughly to remove dust, after which they are placed in an oven set to 110 degrees Celsius and dried to constant mass. When cool, the two fractions are mixed together and then riffled down to create a test sample with a mass of 5,000 plus or minus 5 grams. After the balls and aggregate have been loaded into the drum, the front cover is replaced and secured. The power is turned on. The operative then leaves the room, making sure that nobody else is inside. Locks the door. Removes the interlocking key. Places the key into the control box and starts the test. Nobody can now gain entry to the room without removing the key and unlocking the door. If the key is removed, the drum would stop. Inside the drum is a metal shelf that lifts the aggregate and balls, which in turn causes the aggregate to become fragmented. Each ball must have a diameter of between 45 and 49 millimeters and a mass of between 400 and 445 grams. The test is noisy, therefore anyone directly outside of the room must wear ear protection. The test requires the drum to rotate at a speed of between 31 and 33 revolutions per minute. Therefore, it takes about 15 minutes for the drum to complete the 500 revolutions. On completion, the key is removed from the control box. The door is unlocked. And the operative re-enters the room. The power is turned off. The front cover of the drum is then unbolted and removed. The contents of the drum is then carefully discharged into the tray beneath. All aggregate from inside the drum must be removed. The fragmented material is then taken from the tray and washed over a 1.6mm sieve. It's a good idea to protect the 1.6 by using a coarser guard sieve. This sieving operation is done in several stages to avoid overloading. The retained aggregate is then dried to constant mass, allowed to cool, then weighed. Using this equation, we can work out the Los Angeles coefficient, where m is the mass of the material retained on the 1.6. So in our case, the equation becomes 5,000 minus 4216 divided by 50, which gives a value of 16, as we round to the nearest whole number. The lower the number, the more resistant the aggregate is to fragmentation. For more information on this test, please refer to the standard BSEN 1097 Part 2.